then we get to the next module of the course. Okay, so today's lecture is on variance, bias, underfitting, and overfitting. So I will give a brief overview of what we mean by these concepts, and we try to map overfitting to variance, underfitting to bias, and what we mean by those, and how to improve the metric for a certain model when we are developing that model. Before we start the lecture, I just wanted, I sent a message on Teams that the assignment is going to be posted at around 2 p.m. today instead of 12 p.m. Noon, and it will be due exactly 1 week from today. There are a number of requirements for the assignment, so I would appreciate if you can read them very carefully and try to constrain and try to accommodate all these requirements. So let's look at this outline. Okay, so let me make sure here page display is single page. Yeah. So we are going to look at the notion of machine learning model. We are going to look at the notion of training, validation, and test data, what we mean by them, how do we understand which part is related to what part of the model. I will speak about also the bias and variance, underfitting, overfitting, and generalization of the system for a particular type of model. Machine learning model. So let's look at this slide here. Okay, and these slides pertain, I took it from go back here. Okay, so let's look at this particular slide. So this is how we compute process, how to create a model for a particular process. These are the measurement noise, mostly when we are trying to extract data out of a particular process. And these, the actual process from which we are extracting the model. So this is what we are seeing in real world. So this is the perfect world. This is the perfect process. This is the noise due to measurement, induced noise, and this is the actual process. So as you can see, the actual process is quite chattery. And when we are going to extract the particular type of data, the data might not be 100% expressive of the true model. So in fact, we would like to extrapolate from this particular noisy behavior here, the system that is similar to here, because we know that in real world system, in a perfect system, we don't have this chattery behavior. So we would like to extract the best possible model from a set of collected data, which could predict future occurrences. So we don't want to create a model that is going to follow up all the little jaggedy edges in this particular representation here, because a lot of these jaggedy edges here are related to noise, something that we are not interested in measuring. So we would like mostly to interpolate with a certain type of representation. So there are two types of models that, as we have seen, machine learning models in the literature. So there are the classification-based model, and also there are the regression-based model. So classification when the output of the system is categorical, and the regression is when the data at the outset of the neural network is continuous. In the assignment that I have prepared for you, we have the problems related to the two category of machine learning model, because most of model in machine learning pertain to these two major classes. So for classification, we would like to build a model that separates a system that provide us with a boundary that is able to separate between two or more classes. As we have seen in the perceptron, in the Adeline, we are only able to do two or binary type of classes. For the multi-layer perceptron, we are able to do n type of classes, and that's the power of the multi-layer perceptron model. Moreover, the multi-layer perceptron model based on the backpropagation learning algorithm that we saw on Monday is also able to create nonlinear boundary for the system. The second class, of course, is regression, where we would like to find continuous relationship between two variables, x1 and x2, or between n variables and a particular mapping that is displayed within n variable in the n plane, in the nth dimension plane, using only sample and no prior knowledge of their distribution. So we would like to create this continuous mapping for the system. So we call it regression. And of course, regression, we have seen a lot of regression models in the past. Some of them are linear regression, some of them are polynomial based. But what we are speaking here about is mostly regression based on neural network output. So the output of the system is continuous, and we would like to extract the regression that is leading to that particular mapping. So this is an example for classification. So as you can see here, so there are the blue triangles and there are the reds. So we have two classes and we would like to separate them. If the system is linearly separable, then we are able to create this line or also hyperplane for the system that separates between the various type of classes. As you can see here, this particular line is not able to separate perfectly the classes because one of the classes is embedded in the second class here and two classes here are embedded in the other class. So the linear class is not able to do it. But realistically, when you look at this particular system, it is extremely difficult to separate between these two classes. So usually what we do when we are confronted with a classification problem, sometimes we need to let go of certain type of data that are not well classified. We call them outliers. So this is, we call it outlier in this particular class, and these two could be outlier classes. And we tolerate sometimes small number of outliers because, I mean, to come up with the very, very sophisticated boundary might take us a lot of computational time and resources. As you can see here, for this particular class here, for the same type of model, so if we were to create even more nonlinear type of behavior, still we are confronted with difficulties. We are not able to classify between these two classes using a nonlinear type of model. And then we make the model even much more complicated. And you can see this is a boundary that classifies between the two classes. In order to create this boundary, it is extremely difficult to do it using this particular boundary, and it requires a lot of training, and it requires a lot of computational resources that are required for the system, and the model might never converge even after sometimes hundreds or even thousands of epochs. So we can see here, we can tolerate certain type of classes belonging to one or the other class. Here, nonlinear hasn't provided an improvement over this class, and here is nonlinear, but it is very, very complicated type of boundary. And usually we are not very much interested in this type of boundary, simply because these type of elements that are interlocked into this particular location might be due to noises, and we don't want to model noises. So this is what we call linear, this is quadratic, and this is high degree type of classifier system, mostly using polynomial type of boundary function. Let's look at, so that was the classifier, so trying to get a boundary between the two classes. This is a learning model for regression. So the regression, we have a certain set of points that we have gathered from a particular process, and we try to join this particular type of points so that we create a model which later on could be expressive for a wide range, of representation for additional points. So again, why we are trying to develop these models? We are trying to develop these models in order for us to predict in the future when we have an x1 point that comes in this axis here, we are able to predict the x2 point. So that's what regression does, especially in the 2D space. So regression of data with polynomial function having different degrees of freedom. So this is the representation of a polynomial function. So we can see here, we have a regression that is linear, very simple one, and yet it might interpolate well between this type of data. This is a more sophisticated one, but still we are not able to mingle with all the type of data. This is another type of model, which doesn't represent very smooth type of representation. So here, although the linkage goes from this point to this point, actually it should go from this point to this point to this point, and etc. till the end. So we see that while this system is able to describe and is able to map or join between the various points, we are going to see this is not a good model. This is not a good model to choose. This is an average model, and this is very simplistic model. So we are going to study what we mean by creating a representative model for a particular system. Which one we are going to choose? Is this model, simple one, the average complex model, or the very complex model? And we are going to see that for each one of them, there are some advantages and disadvantages, and we are going to study them next. So that's what I wanted to tell you during what we are going to see in this lecture. So we would like to create a model for classification or for regression that is acceptable, that is good for prediction. And the word that I would like you to remember now, it's good for generalization. What does that mean, generalization? Is not that the system is able to link between the various type of points which are provided to us during the training process, but we would like also to have this model valid for other points that the system hasn't seen before. So this, we call them validation and testing points for the system. We are going to see the meaning of these various connotation, very important connotation that we need to understand and to remember. So classification. So what we would like to do here, we would like to teach, for instance, an example. We want to teach a model here that gives us the difference between a tomato and cucumber. And you know that each one of these vegetables have its own characteristics. Tomato is red, cucumber is green. Each one of them has different type of dimension. So these characteristics that characterizes these type of vegetables, we call them features or attributes. They are going to be the inputs of a particular system. We show it several tomato and say these are tomatoes. So what we are going to do, we are going to show an engine which has a computer vision, possibly tactical type of sensors, and we are going to teach it to recognize these elements as tomato. We do the same thing for cucumbers. We teach it. So this is a supervised type of learning model. So the baby here, us, which are us, it could be one person very, very small. So we teach them how to call these particular vegetables. The same thing apply to an engine that we would like to develop. So the baby can find out whether a new unseen vegetable in the future is a tomato or cucumber. As soon as it sees something that is almost spherical and red, then it says that this is tomato. If it's not, and if it's elongated, and if it's a green, then we call it a cucumber. So the output of classification here is whether tomato or cucumber is known as discrete. So this is the definition of classification, which I provided few lectures ago. For the regression, we want to make an artificial leg for people without legs. So let's say we use electromyography signal in a healthy leg. We collect which signal results in which degree of knee. So the learned artificial leg, when is installed, can estimate the degree of new and learned electromyography signals. So the output of this regression is continuous. So this is an example of how to train a system that we are going to implement for a particular person to create certain type of signals for the inputs of this artificial leg, and then the system is going to provide us with the particular type of action of that particular leg. So this is, AI or machine learning training for artificial leg system. So the output of the regression of the system, the knee degrees, that is displaced when we are subjecting it to a certain type of voltage, is going to be continuous. The same thing, when you are trying to predict the price of a house, when we are providing the system with several type of attributes of houses located in a particular area, for which we know the number of bedrooms, for which we know how big is the backyard, for which we know the area, and we say that the pricing is as such. And then we are giving to the system trained already with the requirements of a particular type of customer, and we tell them this is basically what the expected price for these particular houses. this is a regression system that we train a priori, and then we utilize it to predict particular type of outputs. Let me now speak about something very important. A number of you might be familiar with it, but this is a very important component, and I would like to reiterate it again and again, because you are going to see it in the assignment. You might see it as well during the quizzes. Training, validation, and test data. Sometimes we see only training and test data, but usually these are the three connotations that we utilize. So training and validation are, we are going to define them, are different type of specification for the data that we gather, and test data usually is the final data set that we are utilizing to test that whether our system works or not for data that the system has never seen before. So this is what we define: the training data, validation data, test data. This is the most common type of definition that we are familiar with and that you find in many textbooks. So the data set can be divided into disjoint training, validation, and test set. So when we extract set of data from particular process for which we would like to build a particular model, then we divide the data into three categories. The first one is training, which is used for teaching the model. The second one is validation test data sets for selection of hyperparameters, and the hyperparameters are known to be parameters with which the system operates. And the second is to check the overfitting introduced later in this set of lecture during the training phase. So these are the type of data that the system utilizes to make sure whether the data is valid or not, and the model is valid or not, or how to improve or tune up the model. And then the test data used for testing the trained model. After we do the training and the validation of the model for a set of training data set and validation set, so the system has never seen this tested data, and then we see whether this model is going to be useful or not. So this is never seen by the model during training and cannot affect the weight in any way. So this is how we implement the model, and to basically this is the when we are going to send the model for commercial type of application or for beta tests for a portion of a population that are testing a particular software. So this is developed by the designer, training and validation, and this is developed by an early population for people to test the system. And once the system, after a certain cycle, is tested again and again and again, then we let it go for a commercial type of implementation. So this is usually almost the proportion of what we utilize in training data, validation data with testing data. So usually we have 80% are reserved for training data and validation data, and 20% are specified for the test data. So I would like you to remember these nomenclature for the data sets that we utilize for particular system. Let's talk about now variance and bias. So we have now defined so far regression, we have defined classification, we have defined the test data, we have defined validation data and training data, and now we are going to talk about the notion of variance and bias. So let me stop here for a few moments and see if you have any questions so far. So for those who arrived a little bit late, I mean, to this, I just mentioned that there will be, I mean, the assignment is going to be posted at 2 p.m. today, and it will be due 2 p.m. next week, Friday. Any questions that I might see here on the chat, or you can even speak if you would like? Okay, so if not, then I will continue now with the notion of variance and bias. These also are very important concepts in the area of machine learning, and with it we are able to develop a good model for our system depending on these two types of parameters which are working against each other. Okay. The error in prediction is defined as the difference between the predicted value and actual ground truth values. Two major metrics in direct correlations with the prediction error are then used to assess the goodness of a model. So this is what we have defined when we spoke about the perceptron, what we have defined when we spoke about the multi-layer perceptron, also and what we have defined when we spoke about the multi-layer perceptron. So we have the predicted values that are generated by the engine that we have built, in this case, artificial neural network, whether it's a perceptron, Adeline, Madeline, or multi-layer perceptron, and the actual ground truth. Ground truth are no other than the labels that we have used for the system as target outputs. So these are the real values that we have collected from the system. So we are going to use this type of data to build our model. So two major metrics in direct correlation with the prediction error are then used to assess the goodness of a model. So there is what is known as variance, and there is also known as the bias. Let us look at the mathematical definition of the variance and the bias. So in the statistical term, when we are tackling, a random variable, usually we speak about an expected value for a random process. So here we are speaking of a random process. Why? Mostly because we are dealing with a process for which it has been affected by noise. Remember in the earlier slides what we meant by noise? So noise when we are tracking a particular variable. When we are trying to measure a variable, we induce noise without us wanting to do that. Why? Because these instruments they are not perfect, they are mechanical, they are electronics based sensors, they are corrupted with noise in terms of the measurements. So we have the expected value, of course, the expected value as we all know in the discrete form for random variables. So it's the summation of all the xi times the probability distribution of the probability for that particular variable. So this is the expectation of x, or the expected value. The variance, the same thing, we are defining it as how spread the values of a random variable given by big X. So X is composed of all the element xi's in this particular case. So this is a discrete representation of a variable, and that's why we are using the summation. So it's given by the expectation of the square of the random variable minus the square of the expectation variable, which we have defined already here. So this is the definition of the variance. So look what we defined here, the variance. So the variance is no other than the expectation of x minus ex squared. So it gives us the spread, the values of a random variable. So within a particular type of belongingness of the random variable, how the values of the random variable are spread out. Remember the Gaussian process, the spread of the Gaussian process, and we relate it to the variance. This is similar to that. So the spread over the variance, it gives us the attitudes for this particular system. So when we speak of high variance, so we say that this is, high spread of the values of the random variables. So we are going to see why this component is very important in the in relation to a model that we would like to develop. The bias, on the other hand, it gives us how different the expected value of a random variable is from its actual value. So this is the actual value, and this is, we call it expected value, or the average value if you would like to call it. So the difference between both of them is known as the bias. The bigger is the bias, of course, the bigger is the difference between the actual value of the process and the measured value, because remember, this represented an average or an expected value of the measured component, which is x hat in this particular case. So these are the usual definitions in the statistical type of formats. So let's look at their correlation here in this DART illustration. So the DART example for high bias and low variance. So here we see that this is the center. This is where we would have, very, very good value for an excellent average for the value of the system when they are either well spread out or when they are close to the center of the dot. So why we call it here high bias? Because simply this particular values here is quite far away from the origin. So when we are doing the average of all these red data, we are going to find out something in this cross. So it is far away from the expected values of the system here. So we say that this system has a high bias, but as you can see, the spreads of where the data is located are not far away from each other. So we say that there is low variance, so low variance of the data points. Let's look at the second one. So here we have low bias because when we do the average of all these data points, we are going to find out that it's going to be close to the center of the dot. So you can see here the green levels here. So this is a low bias. So this is a high bias, this is low bias, this is an average bias, and this is low bias. So the B, we have low bias, but also we have high variance. High variance, it means that we have high distribution of the data within a large spectrum of their location. So you see one here, one here, one here, one here. So we go over large spectrum of their distribution. And here we have high variance and high bias. So you can see here the average of all these points is going to be a point which is going to be located in this particular area, which is far away from the center, which we expect it to be. And you can see also the system is quite dispersed. So this is a high bias type of location. So here it's high bias and high variance. And this is not something that we want to do when we are using the dart. However, look at here. So we have all these type of data point clustered very, very close to the center. So we have low bias in this particular case. And also we have most of the data points co-located with each other, clustered with each other, which is low variance. So this is one of the most desirable type of system that we are aiming at. Okay, so the worst and best cases are C, it's the worst one, which is high bias, high variance, and this is the best system here, where we have lowest bias and low variance. The center of the circle is the true value of the variable, and the green double arrow denotes the distance to the center of the average of the predicted value. So that's what this dart illustration. So most of the models that we would like to develop in the future have to have low bias and low variance. So this is what is known as the dart illustration. Variance in machine learning. So let's look at the variance in machine learning and what is its importance with respect to the model building. So a variance is defined as the amount that the estimate of the target boundary for classification or target function for regressor will change if different data points were used. So what does that mean? We would like a system that when we build it from a set of training data points, we would like this system to generalize well for other type of data points that the system did not see before. So what does that mean? We don't want to have high variance. We don't want to have systems that are different from each other, systems that are not operating in the same manner when we measure them with different type of data point set. This is very important. So a high variance, which is something that is not very well desired, is a significant changes to the estimate of the target boundary under testing data. So what does that mean? This is a very important point, and we should not aim to build systems that are of this nature. So what does that mean? It means that we don't want to have changes from what we have built already to the testing data that the system has never seen before. Why? Because we are not generalizing the system. The system is not generalized. The system, we are going to call it in a few moments, is overfitting. And we are going to see the main reason for that. The low variance, however, is something, so this is negative. We don't want it. And for this particular system, we would like systems that do not change much when we are building boundary or when we are building the regressor under testing type of data. So this is what we want to aim. So we want to have a system with low variance in general. We will get back to the bias. For now, that's what we want to do for the variance components. So this is very important to understand because we are going to get back to this representation and description. So variance in learning model. Usually complex machine learning algorithms have high variance. What does that mean? When we are trying to build systems, especially in the start of an engine, using a certain set of data, using a certain set of hyperparameters of the model, usually we are going to confront a system that is not very well trained. A system for the training provides us with very good results, but when we test it, it's a bad system. So we would like a system that is trained well and tested well, okay? So some example for low variance and high variance machine learning models. So I'm giving you here the titles for a number of low variance systems. So linear regression is an excellent type of system for low variance. So this is very good system. However, we are going to see that the linear regression is a bad system for low bias. They are good for low variance, but they are bad for bias. So this is positive from one side, but it's negative from the other side. Linear discriminant analysis, or what we call LDA, is also another type of tool that we are utilizing in machine learning models with low variance systems. Logistic regression is a system of low variance. Naive Bayes classifier also a system of low variance. Of course, we are not going to see all of these systems, but we see the logistic regression, the linear regression. Let's look at the high variance here. Polynomial and decision tree, polynomial regression here, and decision trees are systems of high variance, of course, depending on the polynomial size. Support vector machines, we are going to study them also. They have high variance. Multi-layer neural network, similar to the backpropagation learning algorithm, could be systems with high variance. K-nearest neighbors at the start could be systems with high variance. These systems, why they have high variance, but we are able to improve them. We are able to improve them using what we call tuning parameters, as I'm going to show you in the remainder of these type of slides. So this is what I would like you to remember, the definition of low variance, high variance for machine learning system. We don't want a system with high variance because taking them from the training type of data set to the testing data sets, they are going to perform very badly and they are not good generalizer. So this is what I would like you to remember so far, okay? So let's look now at the notion of bias. So we saw also the bias is the displacement from the average components of these type of data points as we have seen it schematically in the dart representation of the system. A bias is the amount that the estimate of the target boundary for classification or target function for regressor classifies or regresses training data points correctly. So what does that mean? How distant is the estimate of the target boundary? So how far we are for the classification from what the system provided us. For the regressor, how far is the data point far away from the target function? So the estimate, how far it is from the target value for the regressor, okay? Okay, so the target boundary for classification and the target function for the regressor. Classify or regresses training data, so how far we are. And again, when we speak of a machine learning model, let me repeat it here again, we are dealing either with the classifier or we are dealing with a regressor. Classifier is for discrete output, regressor is for continuous output. So high bias when we have, distance between the actual value and the estimate value far away. So we call the system high bias. So this is a bad performance that we don't want to see in a particular classifier or a regressor. The low bias is something that we wanted to see. So this is positive. This is negative. Okay, so now low bias is a good behavior of a system. Low variance is a good behavior of a system. So that's what I would like you to see. Usually, when we define machine learning model, whether it's artificial neural network or is a polynomial system or a decision tree, a lot of the times from the start, we have either high bias and low variance, or high variance and low bias, or we can have also high bias and high variance. So we would like to balance out our machine learning model by having at the end of the day a good bias, an acceptable bias that is low, and an acceptable variance that is also acceptable for the performance of the system. And we are going to see the metrics for defining and for validating this particular type of items. So that's what I wanted you to understand for so far in this particular presentation, and we will go now to a certain type of example to illustrate why we are finding this type of behavior, such as the high variance and such as the high bias, because naturally a system is built with this particular negativity embedded in them when we are training them. So a system in general, when it is trained using training type of data before validation and before testing, usually could provide you with excellent type of bias, low bias after long-term training, but it provides you with very high value of the bias, and we are going to see them in certain type of figure. So going back to that particular example, so as you can see here, so as you can see, so the more we go this way, the bias increases. Okay, so here for this particular system, as you can see, this particular boundary is very well structured to separate between these two type of data points here. So it separates between these particular points and these particular points. So this particular model, we say at first stand, it has low bias classification. But is this model good? It's not good, because we are going to see that this system, while it has low bias, it has going to have very high variance, because this complex particular type of structure, so that is going not to have very good variance later on. This is a medium bias system. Okay, this is an acceptable type of system, but this one is high bias system. As you can see, the distance between these elements and these elements here, okay, the distance between these elements and these elements here. So this is what we call the high bias model for a classification type of model. So this one is not very well advised type of model. So this is for classification, bias in classification. So let's look at the bias in regression. As you can see, the distance between this element and this particular regression curve is these values. So they are quite far away, these elements. Okay, so we see that the system here has a high bias. So this is a high bias model. This particular system here has low bias, because there are no error between the values that with which we have trained the system and the system with which we have built the model. But also we are going to see that this system has high variance, which is not something that we want to see, because later on, when we are going to build values, we are going to generate values for the system, we are going to find them, they are far away from this particular map that we have built. So this is bias in regression. So this is simple model, as you can see, linear here, and this is highly polynomial type of model, which has low bias model. Let's look now at the notion of underfitting, overfitting, and generalization. So we spoke here about several correlation, we spoke here about bias, about variance, about testing data, about validation data, about training type of data. Let's look at the notion of underfitting, overfitting, and generalization in machine learning system. So let's look at this particular example for overfitting. So we start to describe some features of a coffee cup. A cup is like a glass in this stage. Baby, here basically it's here. So this is an example. rhetoric example. Baby is underfitted because of small amount of learning. It confuses glass with the cup. So for a baby or an early learned model. So a baby here is a human, it's physiological, but it could be also a machine learning model at its early stage of learning. So we start to describe some feature of a cup. So we say a cup is like a glass. In this stage, a baby is underfitted because of small amount of learning. So it starts to confusing between the glass and the cup. Then we say that a coffee cup usually has a cup. It has a cup too. So we are increasing the number of features here. Now we have given the baby enough information to provide us a good fit and can generalize to unseen coffee cup. So here, this is very generic. So this is a high bias. So here we are starting to minimize the bias and we start putting a good fit for a baby or a small machine to provide us a good fit. If we go further by giving too much information, the baby gets overfitted. So if we start telling them that the cup has to be 5 centimeters and then it has a cup, it has a certain type of features, then the baby gets overfitted or confused for the physiological human, or even for the complex machine learning model. The system starts to look at that particular description and try to build a model for that very, very restricted description of the description of a cup. You can specify a cup, I mean, in 1,000 ways. Then, in the general case, when we arrive to generalize a coffee cup, then we find that the system is not able to generalize well. Why? Because the system simply has memorized than has learned. So the system is not a good generalizer. So this is a big problem for overfitting. We don't want system that overfit. We don't want system similar to this one here. So let me go back. Yeah. This is an overfitting system. Okay. So this is the description of the cup, very, very specific type of cup. However, if we give a cup that may have certain type of characteristics in this particular edge, the system is not going to generalize well because it has memorized this particular feature for the system. And this is very important that we need to understand at this particular stage. Okay, so going back to the classification for the system, so we have seen the regression. So now we see the, so for the classification. So look at this particular boundary that separates originally between the blue and these orange type of values here. When we have this particular linear or low variance type of model, we are able to fit well some of the type of new data. It's not perfect, but some of the new data is being fitted well. Although there is a high bias here, but the system here has a low variance. Why? Because the system is able to accommodate new type of data that are close to this particular type of region. Even this type of red one, which is an outlier here, the system should be able to accept it. But look, the system here was able to accommodate this particular value. So low variance, it means that we were able to accommodate a model to provide us with good testing data. Remember that this is testing. The system has never seen them. This is testing type of data. This is testing type of data. So the system was able to accommodate reasonably this particular element. So here we have medium bias model. So the system might accommodate to a certain level these new values here, not perfectly, but still is accommodating the blue classes here in a certain way. This is not also a good model for the boundary of the classes, but it is an acceptable one because it has a medium variance and medium bias. But look at this particular system here. So this is a system with low bias, but look how it did not perform well with the testing type of data. Look at this element here, test. Look at this element, test, that is located in this particular area here. Look at this particular element, test. So look at this particular element test. So we see that the testing type of data were not able to generalize well. So this is an overfitting. This is what we call overfitting. So this is bad behavior of the model, and we should get away from it, because as soon as you have a noisy type of data, you are going immediately to find it in this particular location. And this gives us, we go back here to what I described to you in the difference between the perceptron and the adaline. Something I mentioned it before, and let me remind it to you before. The perceptron is able to separate between linearly separable classes, but it provides a boundary. That boundary sometimes is not optimal. Why? Because we have utilized the Hebbian learning. We did not utilize the Woodrow-Hoff learning, which is an optimal type of boundary system. So the adaline generalizes better than the perceptron. So here we are not able to generalize very well the system, and we say that the system has overfit. So every time you say that the system has overfit, you have a high variance for that particular model, something that we don't want. So we would like to have low variance or medium variance and low bias at the same time. So this third value here, so this is underfitting. So we create very simple model. So usually we underfit, and complex model is overfitting. So that's the general idea. General idea, when we have very complex model with possibly small amount of data, we have overfitting. And this is the summary that I'm going to make out of this lecture. When we speak about underfitting, we have a simple type of model, which we would like to make it more complex to try to cover the complexity of the model. So for a system that is complex, a process that is complex, a very simple model, machine learning model, will cause underfitting. So these are items that we need, and we would like to be in the middle. So we would like to have almost acceptable level of bias and also acceptable low of variance. And this is the balancing act that we need to make in the area of machine learning. So the same thing here for the overfitting in regression. So we spoke about the classification. So here you have a number of data points, test data. They are still away from the linear model here. So here we have high bias model, and it's a low variance type of model. So which is low variance model, which is something that we would like, but still the system has high value. So here it has improved a little bit because it's predicting almost an interpolated type of solution. Here the system is of high variance. Again, high variance is bad connotation. So here high bias is bad. Why? So you can see for the testing point here, the system was not able to have this curve go through it. So this is a bad model because our model was very specific, was overfitted. So we overfit the model, and usually overfit happens with two things. First of all, small amount of data that used for the training. Secondly, complex model that you choose for your machine learning model. And we need to compromise between high variance and high bias to have a system that is good for training and good for testing. So this figures is very key, and we need to understand it very well. So let's look at the diagram in training. Okay, so this is training error and test validation error. So when we are building a model, usually we use training and we use validation. So the training model usually is the system that provides us with the several stages for the weight update. But also we try to validate that model to make sure that those parameters that we have developed for the system are not overtrained. So let's look at this particular error, which is due to the testing, training error, and this particular error. So the smaller error is for training and the larger error is for testing. Let me respond to two questions here. Let me stop here for a few seconds and respond to two questions here. Can we only define bias with supervised learning? How would we know if unsupervised learning classifier regresses correctly without labeled data? So we haven't yet, good question, but we haven't tackled yet unsupervised learning, we are going to see other type of metric for unsupervised. So we are going to see the clustering is a little bit different from the supervised learning. So we don't speak of bias and variances into clustering and into unsupervised learning model per se. So for now, I would like you to remember these items here. For the bias and for the variance are related to supervised learning. So that's what I would like you to remember. I'm not going to confuse things. We will talk later on when we tackle deep learning machines, how we can utilize some aspects of variance and some aspects of bias into these type of deep learning. But for now, focus, the bias and the variance are applied to systems that are labeled, systems that are supervised. Okay, so that's what I would like you to remember. Second question, how do we care about the distance between the data points and the classification boundary? Of course, I mean, when we speak of data points in this particular case, we are speaking about something that is created by the training type of data. Okay, so once we create this type of data, we are going later on to make sure that this classification boundary is also a good classification boundary for the testing type of data. So we do care a lot about the distance between the data points and the classification of the boundaries. Because if we are very, very close to certain type of data points that are at the edge of the classification boundary, then in the future, stained or a noisy type of data that might belong to a particular class might go and reside into the opposing class. So this is an important component. We have to be far away, I mean, to classify as optimally as possible between the data points. So the boundary has to be usually, for classification boundary, the farthest away from any of the classes in order for the future, when we are going to generalize, if certain type of data points are corrupted with noise, we don't want to confuse the boundary of the system. I hope I responded to these two questions that have been posed here. So let me go back to this important figure here in this particular representation. So we are talking about this particular error. So this is the estimation error, and this is the model, or so the model complexity. Sometimes we have also we utilize the number of iterations. So model complexity means here model that is too complex, but also we can also have the same figure with number of iteration for a particular model. So you might also end up with particular curve like this one, where here the number of iteration or the number of epoch for particular model, so model X, okay? So for model X, we might have same behavior of the system, and I'm going to show you in a few moments. And you have also for the testing type of data, some behavior similar to it, okay? But let's look at the model complexities here. So the model complexity, when we are overfitting the system, basically we are giving more type of complexity for the structure of the system that is needed. The model is simple, and yet we are trying to overstretch it. So the system is not going to generalize very well. So this, possibly for the training type of data, the error becomes very, very small. But for the testing data, the system is not able to generalize. So going this way, we have low bias, but high variance. So this region is not a good region of the model. This region where you have high error, testing error, and training error, also it's not a good region for the system. This is a good region. This is location where we don't underfit and we are not overfitting. So this is the optimal location. If we are able to be located in this particular area where the training error is small, and the testing error, although it's not very, very small, similar to, I mean, in other places, yeah, this is the smallest actually of the training, but it's not reaching the training type of error, then this is a good region. So this is positive. So this particular area here is going to have the best generalization for the system. So we would like to be located into this particular area where the complexity and where the error meet. So this is the best possible type of system. So here, low complexity, high complexity. We don't want high complexity. We don't want to have low complexity. Here it's a small, it's a large error, and here it's a small error. So we would like to be, and here it's also large error, large error. So in all these regions, we have the best of all worlds. Okay, so this is a positive area where we want to be. So we would like always to have a model that is not extremely complex, that is not overcomplicated, and yet it has good representative behavior. So I would like you to remember this particular concept here in the form of low bias, high variance, high bias, low variance. We would like something in the middle. We don't want it to be we want it to be very good generalizer, and we don't want it to fit the training type of data. Overfitting system is bad. Okay, so the more complex the model gets, if it is not trained by sufficient amount of data, we will have overfitting. So when the model is very complex and the data is small, we have problem. When the model is not complex, even with large amount of data, then we don't have a good bias. So the system is going to be high bias, and we have to be in the middle. So if you are understanding this picture, the diagram, then you have understood major concept in the building of the model. So let's look again at the definition. Underfitting, it means that the model fails to capture the underlying trends of the data and performs poorly on both training and testing set. This is exactly what we are talking about. So the model here is underfit. It has high bias. It may have low variance, but we are not interested in low variance because the error here is very, very large. As you can see, it starts with large error. So for a system that is not very complex, not enough complex, the estimation error is large. So we don't want that to happen. So underfitting happens when the model is too simple. So it could be linear or first order polynomial, or it could be a neural network with one or two type of neurons. The training data is not enough to capture the complete behavior of the process. So for the two cases, when the model is too simple and the training data is not enough. And we are going to see how to salvage this problem later on in the lecture. Okay, let's look at the overfitting and the problems we have with overfitting. So the overfitting, the model corresponds too closely to a training data set. So we have overstretched the training of the model. So let's suppose that we would like to simulate the mapping of sine x. Sine x or cosine x could be simulated with two types of neurons. If you put 100 neurons to over-simulate the system, then the system is not going to be behave very well, because you are overfitting it. You are overtraining the system. So overfitting and overtraining of the system, sometimes they embrace each other. So they are similar to each other in certain type of case, because you go for large number of epochs in order for you to get a very, very good trained model. Sometimes it doesn't benefit you, and it provides you with a high variance type of model. So therefore, performing poorly, the system will perform poorly on the testing set, because the system is not overgeneralizing. The system has been trained mostly over this type of training data set. So the system doesn't have good generalization, which is bad behavior of a machine learning model. So this is a low bias and high variance. This is what I mentioned to you in the early slides when we are located in this particular area here. Sorry, in this particular area. So we don't want to be close to this area. We don't want to be close to this area. Assignment number 1 is going to enlighten you even further when you are going to work on the various type of problems. So overfitting happens when we have a model too complex and rigidly tied to training data. So it has all these type of jaggedy edge for the system. So it is inflexible for the system. So it is well developed for a specific type of data, which is the training data. So we need to evade from that particular inflexibility. Also, it happens also when the training data not containing enough variety to describe the entire population, when the system, when the data is not very well selected, when the data is scarce. When the data is scarce, we have also overfitting. Third one, when we have many training iterations. Sometimes we need to stop the iteration at a particular level when we are doing the testing. So we do not need to train the system forever. This is what is known as overtraining. And this is where the overfitting and the overtraining meet with each other. So they become synonymous. When you are overtraining the system, putting more type of cycles, epoch cycles, than the system requires. You might obtain an excellent training model, but you are obtaining a very bad testing model, similar to what we see in this picture. So here we are overtraining the model with the very model complex model. So similar to here, the number of epochs. We are overtraining it, so we are obtaining very low value of the error. But look at the testing error. The testing error is very high. We don't want that to happen. Mostly we are interested in a good testing error and a good training error, which is basically in this particular location. Okay, so now let me show you this picture that I took it from the internet, and it shows the complexity. So underfitting, so the complexity balance, how we should not have low complexity and we should not have high complexity. You see here, the system is underfitted. This is bad system because it has high bias and low variance. This is a bad system because overfit. It has low bias. You can see that all the points have fitted, but it has high variance. And the system, when we are going to generate new data, the system is not going to be able to go through this particular type of point, and the system is not very well described. So I took this from machine learning at Berkeley, slides, and it shows that we need to be in the middle. We're not very complex model, but not very simple model. Okay. So this is also another type of slide that I would like you to understand. So we have all these type of data points which we would like to describe. So these have been obtained from a particular system. So this, we design it with a system that is somehow minorly complex. Okay, so the complexity is equal to 0.12. So this is complexity 0.96. So for 0.12, you have a system with, so the data collected is in red and the regression model is in blue. So you can see here that the system has very, very high variance, but also it has, so this is low bias here and low variance and high bias. As you can see, the distance between all these points to this particular curve is very, very, very large. Let's look at the bigger, and you can see the error here. So the error for the testing, so the blue is the testing, the red is the training type of data, red versus blue. So here we are located in this particular area, very high level of the error. This is bad system. Let's look at the complexity, 0.53. So you see that we have improved on the description of the model. Here, the error now, they are smaller. So the testing and the training are smaller, but they are getting a little bit larger. So here we have a model that is a little bit more complex, and see the type of error. We went further down to the error. So it's become smaller for the training, and also it's smaller for the testing. So this is an excellent behavior here, okay? And here for very complex type of model, overfit. So we have here very high variance and low bias. So this means very small error for the training, but high testing error, something that we don't want. Okay, so this is we don't want it. This is we don't want it. This we want it somehow, but also this we wanted it even better. Okay, because low variance of the error. So model A is simple, high bias and prone to underfitting. Model D is complex and prone to overfitting. Model B and C are better generalizer of the data. So these are two better models that we might utilize and we might use as the representative of the model. This is similar for this model 1, this is model 2, model 3. Also this I took it from the internet. So this is for model 1, this is model 2, this is model 3. This is for the training type of data. And this is for training. So this is training, this is testing. So you can see here, model 1 is here, model 4 is here. So these two are bad. So these have large errors. So we have here underfitting. Look at 3 and 6. 3 and 6, we have an excellent type of boundary here, but this boundary, we don't want it because it's inflexible. Look what happens when we are testing it. Look at this particular type of data here, here, here. So they are outside of the boundary. So we have model 3, this is overfitting. Model 6 here is overfitting for the test of data. So model 3 provided us with excellent training data, but we don't want it because for the testing it gave rise to this particular large model. So the best model here, we found it to be model 2, which has, this particular area where we have medium complexity and medium values for the testing. So this is the two model 2 for the training data and model 5 for the testing data. This is excellent, so we put it positive here. This is negative because here it's bad and these are bad. So negative, negative, negative. Okay. How to avoid underfitting and overfitting. So there are ways here to tackle these particular aspects here, and I would like to express them quickly for you. So there are several ways for creating a trade-off in machine learning. So that's the word that I would like you to remember, trade-off. You don't need to have an excellent training model, but at the same time, you have very bad testing type of model. So solve for the underfitting. So there are two means. We add more training data to the system to capture complex behavior of the model. Instead of linear, make it nonlinear. Make the model more complex, adding nodes, layers in the artificial neural network, or use higher order polynomials if we are dealing with regressors using polynomials. For the overfitting, there are several techniques. So we can utilize the cross-validation. We can utilize the training with more data. We can simplify the features, cis dimensionality reduction, which we are going to look later on in the course, minimize the attributes of the input type of data, early stopping, very important components. Okay, so the cross-validation and the early stopping are two major components. Regularization as well, how to improve the behavior of the model, how to minimize the hyperparameters of the system, ensembling and ensembling, so we are not going to speak about it, but this ensemble, basically you put several type of models that are cooperating with each other, we call them ensemble. Or putting a less complex type of model. Instead of having 100 neurons for sinusoidal or cosine function, you put only 2 or 3 type of neurons. So these are some of the various type of techniques that people have utilized for this particular representation. Again, early stopping, which is very, very powerful technique, is where we train the system and then we try to validate the system. So this is training, this is validation. So the error is the green error. So for early stopping to avoid overfitting. So for each, forget about the k-folds, the sweet spot model exists just before the validation testing errors start increasing. So basically what you do, you start training your model with the training type of data. At the same time, you validate the model with data that the system hasn't seen in the training type of data. And then both of them start decreasing. As soon as the testing or the validation type of errors start increasing, then you stop the training and you say that this particular model is the sweet spot or the equilibrium position for me where I have minimum value of the training and minimum value for validation. This is a system which is balanced, so you don't need to increase variance and you don't have to be in this particular area where the bias is large. So this is an important figure, and I would like you to remember it. So the early stopping is where when you train. So remember, you run the training error and the validation error at the same time. After you build the model with the training type of data, you validate it, and then you build it and then you validate it, build it and validate it, until you start seeing that the validation error is becoming larger and larger. Then you stop and you go back to the system and you say that in this particular area, we have the sweet spot for my particular model. So early stopping to avoid overfitting, pick a model M and run the training and validation at the same time. This is what I just mentioned to you. Validation using the model that was trained in the most recent iteration. At certain point, the validation set is not improving in terms of low error performance, while training of the data in terms of low performance issues, why the training keeps error decreasing. We don't want training error to keep decreasing. We would like both training and testing validation decreasing at the same time. Stop the training and pick the model that led to the lowest validation error. That's your particular model. This is known as early stopping. Okay. Repeat the process with different models, different number of nodes or different regression parameters, and get the lowest possible error for the system. The model that gave you the lowest particular error is the model that you should select for your particular system. This might become very helpful for assignment number 1. Cross-validation, so let me end the lecture with the cross-validation. The model may contain some hyperparameters which need to be optimized without using the test data during validation. So the validation is used for this. So the test data is something that we hide from the system. So there are two sets. The validation, it's like an early testing type of data. And then the testing is the final set of error. Remember, we have the training, and the training is divided into validation and training. And here we have testing. Okay. What is cross-validation? Cross-validation has become very, very important in the field of machine learning system to deal with the various characteristics and various problems of machine learning overfitting. So we divide the full training data into k equal portions, taking one portion for validation while the rest is used for training. The portion is moved, and finally the model is retrained by the parameters with the best validation performance. Let me show you this particular figure. So this is the original training data. So what this means k folds? So basically we divide the training type of data into k portion. One of them is going to be the validation data. The other one is k minus 1 training type of data. So we utilize the k minus 1 here, training the data to create the model, and then we try to validate it, and then get the error for the validation and the testing. And then we do the same thing. The second portion is going to be taken as the validation data. The other part is the training. And we continue. It gives us folds, k sets of models. Each one of them represents one particular model. Okay, so this is what is known as the k-fold cross-validation. So model 1 here and model 10. Okay, so we run all these type of models. For each one of them, we have a set of errors, and then we take the average error as we are doing it here. So this is the training type of data. So we have the gray one is the validation set. This is the set of data that we have gathered from the system. So you can see here, we have 3 k validation. So the first 2 here are used for training. So we build the model and then we evaluate it using the validation. Here, we take this one and this one for training, and then we utilize this one for evaluation. And here we use the training, and here we use the evaluation. And then what we do, for each one of the model, we create the error, and the average error is the average of the k-fold cross-validation for this particular network. So this is what it means by k-fold cross-validation for a particular system. And then you choose the model you want to test for this particular system. So for each model, run k-fold validation and average out the validation error. So here, when we speak of each model here, it means a system with a particular number of nodes. So for each one, you have a model. For each one of them, we run the k-fold validation and we take the average, and then we decide on which best model we have obtained for this particular system. The model with the lowest average of the k-fold validation error is the model to choose, and on this one we do the testing of the data for our model, the testing data that we have never seen in the past. Okay, so let me take one or two questions before we leave here. So there is a question: when we say train with more data, is it higher quantity or variability of the data? Good question. So quantity is important, variability of data is also important. So the quantity means that we are going to increase the spectrum of the data, and this type of data has to be well distributed within the operating condition of the process. So you don't want to increase quantity within a certain region of the process. You would like to increase the quantity, but it has to be spread out. That's the variability of the data, and that's the higher quantity. So we need to do that when we always try, we have to have more data. Very good question. So variability is, related to the basically to the characteristics of the data themselves, and the quantity is the number of data for particular type of system. Okay. Any more questions? Okay. So sorry, I'm not sure I understand k-folds. Okay, so let me go again here very quickly because yeah. So the k-fold simply, you divide the training data into segments. Okay, so segments. So in this particular case, k segments. So then what we do, you take these k-1 segments, you build with them model. And then you test this model for the remaining segments. And then you redo the same thing. So now this becomes the training part, and this one becomes the validation points. So you do it for all the k-folds. For each one of them, you have a model. And for each one model, you have error for validation and error for the training. And then you try to average out the errors for the validation and the error for the training type of data, and you would like them to be as minimum as possible. That's what it means, k-fold validation. So I will post some more material related to the k-fold cross-validation. I will put a link, and I will explain this a little bit more, next lecture. So are there k models? No, there are k models, for validation and testings. Yes, you have k models for validation. That's what we call them models. So this will constitute a model. The training type of data here constitute a model. So yes, you have k models for the k-fold cross-validation. Yes, you are right. There are k models, but ultimately, at the end, we are going to average out summation divided by k, the error. And this particular model, the bigger model that with which we have utilized this system, when we speak of a particular model, we speak the system with a particular set of nodes. That particular model is the big M. So we can call it big M model, characterized by a certain number of nodes. And each one of them here, related to the case, is M1, M2. So they are submodels MK models, for which you are going to take the average to say that for this model with a certain number of nodes, we have this average error for that particular system. Okay, so this is how you create this particular model. And now you don't create any average of the models themselves. These are only to provide you the error. The model is this particular model that you have selected. This is the one on which we are going to do the testing. Okay, so for this particular model, you run the k-fold validation, and then you create another model, and you do the k-fold cross-validation to make sure that the system, at the end of the day, is the optimal one, is the system with the least error due to the k-fold cross-validation type of system. I will explain this because this is going to be part of the assignment, and it will be very well explained for you during the text of the assignment. How do you combine the various K model, as I just mentioned it? So you create a model as normal, then you do K-fold validation to find the error. Exactly true. So the K-fold cross-validation is for the error testing for that general model that you have selected. And then the lowest error provide you, the lowest ever error provide you the best model that you have selected from the number of nodes that you have selected for the system. So when you work on the two problems for the assignments, you will come very much, familiar with the K-fold cross-validation, and I will post additional material on this particular aspect, and I will speak about it as well on Monday. I have to end because I have a meeting in few moments here, but if you have any questions, please feel free to send it through Piazza or to send me by email, and I will be happy to respond to you. Thank you very much for attending today's lecture, and I'll see you on Monday. Have a good day.